Okay, 2.25, we want to sort of check orthogonality between the bound states and scattered states. So we have our bound states and we have our scattered states. Proving orthogonality is just a matter of showing that sort of the infinite integral of psi star times psi, where one of these is the bound state, one of these is the scattered state, is sort of going to give us 0. So let's do that right now. So the integral from negative infinity to positive infinity of, let's start with psi of x, so this is going to be square root m alpha over h bar times e to the negative m alpha magnitude x divided by h bar squared, and then multiplied by psi, the other psi of x, a e to the ikx plus b e to the negative ikx. We close this off with dx, and we want to show that this integral is equal to 0. So immediately, I recognize that I have absolute values here, which instantly means I want to split my integral into two parts. So let's do that first. First off, we pull out the square root m alpha over h bar. And then what we have now is starting with the negative integral, so from negative infinity to 0, e to the, let's see, x is always going to be negative, and we want a negative at the front, so this is going to be m alpha x divided by h bar squared, and then a e to the ikx plus b e to the negative ikx. And the scattered state is actually a little bit more complicated. So it equals a e to the ikx plus b to the negative ikx when x is less than 0. But it then equals sort of the same form but with different constants, f e to the ikx plus g e to the negative ikx when x is greater than 0. So once we split it apart, this is actually going to be plus the integral from 0 to infinity, and now we have e to the negative m alpha x divided by h bar squared, and now multiplied by f e to the ikx plus g e to the negative ikx. And we close this off with the dx, and we close our integral. Now we just have to resolve these integrals. So let's start with this first. So this is going to be an integral from negative infinity to 0, and then what do we have? We have a e to the ikx plus m alpha x divided by h bar squared, and then we have plus b e to the negative ikx plus m alpha x divided by h bar squared dx. We can combine terms here, and sort of, since this is an integration in terms of x, we can sort of split out the x and keep everything else as sort of a constant. So negative infinity to 0, and then we have a times e to the x times, let's switch the order here. So m alpha divided by h bar squared plus ik plus b times e to the power of x, and then m alpha divided by h bar squared subtracted by ik, closed by dx. And just to make things a little bit nicer, let's sort of combine the resulting fractions. So this is going to give us negative infinity to 0, a e to the power of x multiplied by, let's see, m alpha plus ik h bar squared, all divided by h bar squared, and then plus b times e to the power of x, m alpha minus ik h bar squared, all divided by h bar squared, and we close this off with the dx. And now we just have to solve this. So this is going to give us, let's see, a multiplied by h bar squared divided by m alpha plus ik h bar squared, multiplied by e to the power of x, and then m alpha plus ik h bar squared divided by h bar squared, and then we have plus b multiplied by h bar squared over m alpha minus ik h bar squared, and then the same exponential, e to the power of x times m alpha minus ik h bar squared divided by h bar squared, going from negative infinity to 0. So let's see. The e to the x terms are going to both just go to 1 at x equals 0, and they both also go to 0 at x equals negative infinity. So this is in reality just equal to a times h bar squared over m alpha plus ik h bar squared plus b times h bar squared over m alpha minus ik h bar squared. And that is the first part. Next, let's do this integral. So I'm actually going to copy and paste this and move it down. Okay, this is going to give us an integral from 0 to infinity of e to the, let's see, f at the front, e to the negative m alpha x divided by h bar squared plus ikx plus g times e to the negative m alpha x divided by h bar squared minus ikx dx. We're going to do the same thing as before, integral from 0 to infinity. Let's see, f times e. This time let's bring out the negative x at the front. So negative x and then m alpha over h bar squared plus ik, or in this case I suppose it would be minus ik, and then plus g times e to the negative x and then m alpha over h bar squared, this time plus ik. Once again, we combine these fractions to get an integral from 0 to infinity of f times e to the negative x and then m alpha minus ik h bar squared, all divided by h bar squared, and then plus g times e to the negative x. Combining this one, this is going to give us m alpha plus ik h bar squared, all divided by h bar squared. Close this off with dx. Now we solve this integral. This is going to give us, let's see, negative f times h bar squared over m alpha minus ik h bar squared, and then e to the negative x m alpha minus ik h bar squared divided by h bar squared. And then we have minus g times h bar squared over m alpha plus ik h bar squared, and then e to the negative x times m alpha plus ik h bar squared divided by h bar squared. And from this point, we're evaluating this from 0 to infinity. So at infinity, both of these exponents go to 0, and then at x equals 0, both of these exponents go to 1. So what we really want is sort of the opposite sign in front, and this is going to evaluate to just f h bar squared over m alpha minus ik h bar squared plus g times h bar squared over m alpha plus ik h bar squared. So now we just have to plug everything in. So what we're going to get is the square root of m alpha divided by h bar, and then multiplied by these two results. So let's copy paste these. And then close it off with a plus sign in the middle, like that. And then we have some like terms here that we can combine. So this is going to give us the square root of m alpha divided by h bar multiplied by, let's see, this is going to give us a plus g times h bar squared over m alpha plus ik h bar squared, and then plus b plus f h bar squared over m alpha minus ik h bar squared. Okay, we have a few problems here, or we have one main problem here, which is that this obviously doesn't seem to equal 0, and we do need it to equal 0 to sort of prove orthogonality. Now, the solution to this is that we're going to invoke sort of the conditions we sort of found for a, g, b, and f sort of back when we were still solving earlier in the chapter for the delta function well. Because sort of we applied the continuity rule for psi, and we also sort of applied the discontinuity rule for psi, for the derivative of psi in the case where the potential was infinity, and we found that we have two conditions. We have condition 1, which says that f plus g is equal to a plus b, and then we have condition 2, which is that f minus g is equal to a times 1 plus 2i beta times, or minus b times 1 minus 2i beta, where beta is just this constant that equals m alpha divided by h bar squared times k. So from first glance, this doesn't really seem to help us that much, but we can sort of massage our equation to get something more in the form of f plus g and a plus b by sort of combining these terms. So immediately, the first thing I'm going to do is I'm going to distribute out the h bar squared. So what we really have is h bar square root of m alpha, and then we have a plus g divided by m alpha plus ik h bar squared plus b plus f divided by m alpha minus ik h bar squared. And now I can combine these two terms, and what I'm going to get now is h bar square root of m alpha, and then let's see, a plus g multiplied by m alpha minus ik h bar squared plus b plus f multiplied by m alpha plus ik h bar squared. And then at the bottom, this is a complex conjugate multiplying by itself. So this is going to be m squared alpha squared plus k squared h bar to the power of fourth. And now, really the only thing we're interested in is the top terms. So let's multiply this out. So term number 1 over here, this is going to give us a times m alpha minus a times ik h bar squared plus g times m alpha minus g times ik h bar squared, and then we're adding b times m alpha plus b times ik h bar squared plus f times m alpha plus f times ik h bar squared. And let's see, there is a few things, there are a few like terms that we can connect, that we can sort of combine here. So immediately I see sort of a m alpha plus b m alpha. So this is going to give us a plus b m alpha. So that cancels out this term and this term. Immediately I also sort of see g m alpha plus m plus f m alpha. So this is going to be f plus g m alpha, and I'm going to cancel out these two. Let's see. We also have ik h bar squared negative a plus b. So we're going to do plus negative a plus b ik h bar squared. And then we have plus f minus g ik h bar squared. Okay, immediately we know that a plus b equals f plus g, so these two can combine to a single term. We might as well, let's just call it like 2 times a plus b times m alpha for now. And then we have plus negative a plus b times ik h bar squared, and we have f minus g ik h bar squared. Well, that sort of can be redirected in terms of a and b, because remember from our property number 2 over here, f minus g is equal to this thing. So if we write that out, then this is going to be actually plus, let's see, ik h bar squared multiplied by a times 1 plus 2i beta minus b times 1 minus 2i beta. And if we fully write this out, because we know that beta is equal to m alpha over h bar squared times k. So what is this going to give us? This is going to give us 2a m alpha, I'm just writing out everything now, 2b m alpha minus a ik h bar squared plus b ik h bar squared plus a ik h bar squared 1 plus 2i beta minus b ik h bar squared 1 minus 2i beta. Or, yeah, okay. So at this point, we have everything at the front, which stays the same. So 2a m alpha plus well, actually, it might save me some effort if I sort of expand this out fully first. So this is going to be aik h bar squared plus, or not plus because the two i's make a minus. So minus 2a ik h bar, no more i's, 2a k h bar squared beta minus b I k h bar squared plus, or two i's make a negative again, so it's minus again, 2b I, no I, 2b k h bar squared beta. Yeah, okay. So let's see. Instantly, we have a negative aik bar squared that cancels with a positive. We have a positive bik bar squared that cancels with a negative. So what we have left is 2a m alpha plus 2b m alpha minus 2a k h bar squared. And now let's rewrite beta as m alpha divided by h bar squared k minus 2b k h bar squared m alpha over h bar squared k. Immediately you should see that the h bar squared k's cancel, so what we're left with is 2a m alpha plus 2b m alpha minus 2a m alpha minus 2b m alpha. So these automatically also cancel each other out, so the final result is 0 over a bunch of garbage at the bottom that doesn't matter. The final result is 0, therefore we have sort of proven orthogonality between the scattering states and the bound states.